Climate Sciences, School of Marine Sciences, School of Policy and International Affairs, Business School, and the Center for Ocean and Coastal Law at the University of Maine. He has led more than 55 expeditions to some of the remotest polar and high-altitude reaches of the planet, for example, Antarctica, Greenland, Himalayas, Tibet, Andes, subantarctic islands. He has more than 450 scientific publications, received numerous honors, including the first International Award and Medal for Excellence in Antarctic Research, the Explorers Club Lowell Thomas Medal, honorary PhD from Stockholm University, honorary fellow of the American Polar Society, a fellow of the American Geophysical Union, American Association for the Advancement of Science, and the Explorers Club Fellowship. He developed and led major international and national climate change research programs in Antarctica, Greenland, Asia, and New England, and worked with outreach entities such as the American Museum of Natural History and the Boston Museum of Science. He has released 2 popular books and has appeared hundreds of times in the media, including multiple CBS 60-minute broadcasts, several Nova Films, NPR pieces, and the 2014 Emmy Award winner, Years of Living Dangerously. And without further delay, let me introduce.
Thank you, Alex. Thank you. So you're probably thinking after that,
Let me switch.
what in the world does a person like this have to do with lead? As I was sitting in the audience after all of these amazing presentations, I thought, how in the world can I come up with a segue between my presentation and what you've just heard, which is very startling and extremely important. Well, I'll leave you with, whether or not you listen to anything else that I have to say, I'll leave you with one of the big things that we found. The atmosphere of the chemistry of the atmosphere, which we have been exposed to over the last few decades, is absolutely unprecedented in the last million years. And I can say that without a doubt because we know how far back we have records that go. And I can say it's probably unprecedented in Earth history, but we'll be conservative and just say the last million years. So I've spent a great deal of my life living outdoors in very extreme places. I've been very fortunate to be able to do those because in those very extreme places, in the middle of Antarctica, for example, when the wind stops blowing, you can actually hear your heartbeat in your ears. The air is so clean that you for the first time, at least in my life, you feel as if you're taking in air, not halfway through your lungs, but through the bottom of your lungs. And if you get up to just a small bit above the surface elevation, you can see the curvature of the Earth, which is something that only the early explorers got to see. So yet again, another reason why you would think, what in the world does this person know about lead? Well, as it turns out, in places like the Antarctic, Greenland, the Swiss Italian Alps, which we'll be talking about, there are ice cores. And these ice cores are cylinders of ice from which we are able to derive very exciting records. My job here is to really tell you how we get these records and introduce you to the presentation that Alex will be giving, which describes one of these records in terms of its significance to lead. Notice that the people on the right collecting this core are covered in clean suits. The concentrations that we look at of anything in ice are very, very low. That sounds, again, like a contradiction, but you want to go to the outer edges of the world, the remotest places, in order to see the fluctuations and to determine how much of the planet has actually been impacted. Ice cores, which we collect all over the world in these red dots, provide us with a tremendous amount of information: temperature, precipitation, the chemistry of the atmosphere, sea ice extent, volcanic activity, meteorite activity, biological productivity in the ocean and the land, sea ice extent, and a variety of other things. And the thing that we look at the most actually is the atmosphere and what is transported in the atmosphere. And we can chemically fingerprint the atmosphere. This is a beautiful animation put together from real satellite data done by NASA. And all that they've done, these are cloud patterns, and what they've done is to colorize these cloud patterns. So this is sea salt moving around the Southern Ocean. one of the dominant, but not only chemistries in this area. This is biomass burning, green coming off the Amazon, parts of Africa. This is Saharan dust making its way all the way into North and South America. And actually, I found out recently, all the way to Oklahoma. And then you see this white stuff up here. This white stuff is sulfuric acid, one of the two primary components of acid rain. So in an ice core, you can, by drilling down and understanding where you are, like a series of tree rings, go back through time and look at the changes in the chemistry. That allows you to tell differences in the source region, differences in the types of emissions, whether they're anthropogenic, dust coming off the land, volcanic activity. But the atmosphere also transports heat, it transports moisture, and it transports pollutants, the things that humans put into the atmosphere. It impacts surface ocean circulation by causing waves, and it has the potential for causing extreme events, which I'll mention briefly, not because it has to do with lead, but because I want to tell you something else startling at the same time. So in the places that we've worked and our colleagues, you can understand abrupt climate change, which is something I'll mention for a second, because in many ways I wouldn't say it's as shocking as lead, but it's something that's important to know about. Acid rain, lead, which I'll talk about obviously, uranium. We discovered a 10 to 100 times increase in the levels of uranium transported to the Antarctic Peninsula over a 35-year period because of the existence of the second largest open pit mine for uranium in the world. We discovered Chernobyl, an event which occurred in the Siberian region of the former Soviet Union, was transported through the upper atmosphere and for the first time ever discovered at the South Pole. We worked on the Antarctic ozone hole, water resources, Arctic warming, disruptions to civilization with my wonderful colleague Mike McCormick and Alex Moore and others, drought, a variety of other things, and you can read them all. So the work that we do is based on a tremendous amount of technology, tremendous amount of effort by many people. But in the case of lead, it really started with just 2 or 3 people with relatively primitive tools. And certainly Morozumi was one of them. The other 2 that I knew very well, or know very well, Claude Boutron and worked with Claire Patterson. And what they did was to take a chunk of ice from a glacier, clean it extremely carefully, taking hours, if not days, to clean it, and then put it through instrumentation in order to determine what the lead levels are. And you already saw this plot from Phil Landria, and it demonstrates the dramatic rise in lead. In this particular case, it's an Antarctic core. That's very important because the Antarctic is about as far as you can get from industrial sources, therefore lead travels. It has southern hemisphere sources, but it also can travel fairly long distances. And then the idea that the lead levels have dropped off back through time. And no matter how detailed the records have been up until recently, it's actually never been possible to tell, is this a natural level? This certainly isn't, because it's higher than that one. Is that the natural level? And ice cores provide you with that perspective. We have, with our colleagues, also been able to demonstrate, in this particular case, ice cores in Yukon Territory, which is downwind from China, Greenland, downwind from North America, and core from the European Alps, which tells us about the European Alps, that the dramatic increase in lead starts at the turn of the century, and particularly right after World War II. You can see it in the core that monitors China, the one that monitors Europe, the one that monitors North America. Then you see something that is very impressive, the impact of the Clean Air Act, already mentioned, where lead levels begin to drop off. And because ice cores don't lie, unlike a lot of other things, you can also see when the Clean Air Act was first obviously utilized in North America, following that in Europe, and by the time we collected our ice core in China, monitoring China, it was still only the year 2000 and lead levels were still high, and they are relatively high still. So you can use these for a variety of ways to understand the importance of lead, the perspective that one gains from lead. So what we've developed is a new tool that allows us to look at even finer and finer resolution, which in the past was typically as bad as one sample every few hundred years, then it got almost to a sample every few years. And this is a system that we've put together without a great deal of description. We only built this, that thing is dead. Yeah, oh, the battery's dead. Whoops, okay. Thank you. So we only built that little cell, but that little cell allowed us to be able to, thank you, perfect. That little cell allowed us to be able to do some amazing things. We could take what used to be fewer than 100 sample levels per meter. For each sample level, you can do many different measurements, and we converted that, and I'm just being conservative here, to more than 10,000 sample levels per meter, which means you can go back in time when the ice is highly compressed, and you can do a variety of other things that one was able to do. So a program that I was heavily involved in for many years was called the Greenland Ice Sheet Project. This is a bit of a departure, but it shows you how powerful this laser system is, and it introduces you to something that you really should know about if you don't. This is the longest record ever recovered from an ice core in the Northern Hemisphere. It completely changed the way we understand the world. It demonstrates, and this is going from 0 to 100,000 plus years ago, that and the plots are of basically dust coming off the land, sea salt coming off the ocean, and the tremendous variability in here is telling us that atmospheric circulation patterns are turning on and off really fast, and the temperature goes on and off really fast. And in fact, some of these changes occur in less than a year. Some of them are several degrees centigrade changes in a particular region, and then we go into this relatively quiet period, which we've lived in for about the last 11,500 years. The fact that we were able to demonstrate, it's now been verified many times, that the climate can change that quickly was a complete change for climate science. Before that, it was assumed that it operated very, very slowly and linearly. So what we did was apply our laser technology to this transition, the last gasp of the Ice Age, which is right here. It goes into the modern climate called the Holocene in just a couple of years, which is remarkable. It's only based on 16,000 data points at that time, which was the best we could do. And you can see the number of data points that actually refine that. So what we have been able to do with this laser instrument is to go to in this particular case, I'll show you 4 years of record before the end of the last vestiges of the Ice Age, the transition going into 2 years of modern climate, and this is a place where we're now able to get 500 to 1,500 samples per year. And the big story here is the low values basically tell us the length of the summer. In less than a couple of years, basically, this portion of the Arctic and much of the Northern Hemisphere had a doubling in the length of the summer. This is extremely important for a variety of reasons, including disease, obviously. And if you take a look at the modern situation in the Arctic, the Eastern Arctic, in less than 5 years, has actually doubled in the length of the summer. So one of the important things we've learned is now, we discovered abrupt climate change, and we now understand that with the warming of the Arctic, we have experienced the very first abrupt climate change of the modern era. And this will continue, and this is the way climate will change in the future. So this was just an example of what you can do with this laser system, because the very exciting thing that you've come to hear is what we did with the laser in the lead record, and Alex will tell you about that. 2013, as introduction to Alex's presentation, a whole group of people from a variety of institutions in Europe and the United States recovered an ice core from the Swiss-Italian border. And Mike and I had met already, and we thought, wouldn't it be fantastic if you could take the absolutely detailed records that he and his colleagues work with and actually find an ice that could speak at the very same level, literally down to the, not quite the daily, but maybe the subseasonal level. And We worked in a place that people had worked before. They'd only been able to go back 200 years by counting annual levels. And they used a technology which looked like this. By using the laser technology, we could actually pick out the years. Very important, because if you're trying to correlate with the historical record that is spot on to date, and you see something anomalous that you want to try to explain, then what you need is a very detailed record. We took all of these multiple elements that we had, were able to actually assess where the air masses came from, and this is a much better picture that shows you, we could tell the difference between air masses coming off the west, which would, if there were any sort of activity, anthropogenic activity going on throughout Europe, have picked up those pollutants, and versus air masses that are coming off the Sahara that carry dust. And we were able to demonstrate how long, how consistently, and how much humans have introduced lead to the atmosphere. So with that, I'll turn it over to Alex to describe what we found in this ice core.
So I'd just like to say a few words of introduction to Alex, who has spent a lot of time and effort putting this remarkable and very diverse group of scientists and scholars and thinkers together. Alex came to the United States as an immigrant under his own power at the age of 17. He wound up getting his bachelor's degree from Washington University, and then had the idea of applying to come and do a PhD at Harvard University. He was initially most drawn to our colleagues in the Department of History of Science, but right from the beginning, when he came to interview with them, he wanted to meet with people in the Department of History, most notably my beloved and late colleague Angeliki Layu and myself. And so Alex decided to do a PhD between two departments, History of Science and the Department of History, with the full support of both departments, and spent much of his entire graduate career fighting with the university to allow him to do not the requirements of one department, but all requirements of both departments at the same time. He's a man of great determination, and he was ultimately successful. He did a dissertation in 2014, which is a remarkable contribution to the economic, cultural, and social history of the Republic of Venice, in which he was able to demonstrate that the Republic of Venice developed from a Byzantine model, a model from Constantinople, from the Byzantine Empire, the first public health system of a Western European state, which would not be equal for a long time to come in the future. He also developed in this period policy interests. The late Senator Kennedy was fascinated by his discovery that the Venetians, 1,000 years ago almost, had developed a public health system when the United States was having great difficulty contemplating that in his lifetime. Alex completed his dissertation. He won this wonderful postdoc at the Science of the Human Past Climate Change Institute joint project of the Historical Ice Core Project, and last year and this year has led us all in two really epochal publications on the history of lead, atmospheric lead pollution in Western Europe from our new ice core data that could only be read with the amazing technological breakthrough provided by our colleagues in Maine. Alex.
All right. So, we've been talking about lead levels a lot. And we've been talking about what's natural and what's not. And, well, is there a natural level of lead in the air? We don't know. And so we started by looking at our record. Lead, as Philip has already indicated, lead has been with us for a long time. It's been in, and as Jessica has also indicated, we have spread it all over the place. It was used for utensils. It was used for lead pipes from the Roman Empire to Flint, Michigan today. It was used to insulate roofs. And it was used in coinage, as we heard yesterday. It was found in mines along with silver. And as the economy, as we just published an article in the prestigious journal Antiquity, as the economy switched from the gold to the silver standard, lead pollution increased because you had to smelt the lead and the silver together, and the emissions ended up in the atmosphere. Lead, of course, comes from industry, and it comes also from gasoline, and all of that lead has, of course, deposited in the ground, as Professor Reyes has pointed out. Many governments, to this day, mandate the maximum exposure levels are based on the assumption that pre-industrial levels of lead pollution were in fact natural or safe even. They say these standards continue to be continue to be adjusted downward with the work of Bruce and Philip and Jessica and Professor Schwartz and many others. But as we look at the policy, we find this idea that in pre-industrial times, before 1800, let's say, there was an idyllic, beautiful period of human history when the air was beautifully clean and nothing happened. Natural levels of lead were safe levels of lead. And we see this repeated over and over again. Medieval levels are safe levels. Natural processes produce, this is in the UN Environment Program, just one of many other similar documents. And what they used to argue that there was a natural level of lead in the air are publications such as this, Richardson et al., 2001. I was curious what that meant, what that was, and I looked it up. It kept again saying natural levels are safe levels, and this is cited 37 times in the UN Environment Program assessment from 2010. And this is prepared by this fellow and funded by the International Lead and Zinc Organization. You can read the other ones. These are lead lobbies, okay? That is where the idea, the myth of a natural level of lead in the air comes from. So we looked at the lead record from the glacier in the heart of Europe, in the place where Western civilization developed for the last 2,000 years. And we extracted the ice core, and we started analyzing it. And this was the first plot we looked at. It was lead over depth. And there were some drops. There were some very serious drops. There was a baseline, and there were some serious drops. And the first thing we looked at were the drops, and what is that? And so we asked our esteemed colleague, a Swiss-German colleague from the University of Heidelberg, to put a timeline on it. And scientists think, well, climate scientists think in centuries, not decades. And so he put this timeline on, and it started really being suspicious, and Mike and I are thinking, and we're smiling at each other and thinking, oh, that's 3/4 of the way. I think that's a pandemic. I think that something's happening there. And in fact, it was a drop of 5 years to zero, to undetectable levels, I shouldn't say zero, to undetectable levels for 5 years in the atmosphere of Europe. A drop in lead levels for 5 years. And it occurred again in the mid-1400s during another series of epidemics, now pandemics. And that's why the level is not as severe. And here you can see the peak and the abatement after the Clean Air Act. So what is Black Death? Very quickly, the Black Death was the largest pandemic to ever ravage Eurasia, with a 40 to 60% death rate. It is due to this critter, the Yersinia pestis bacillus, and that's all you really need to know. You need to know that 40 to 60% of Europe died because of the Black Death, the largest pandemic to ravage Eurasia. To tell you what a 40% conservative 40% looks like, that's what it looks like. It's everything west of Chicago. Imagine that, what that would do to your society today, right? And so, what did that do to this? What did it do to lead pollution? What did it do to lead production? Well, it stopped it completely for 5 years. For 5 years, lead production in Europe completely stopped. There it is. And so we wanted to find this, corroborate this with historical records, because that's what we do in our crazy enterprise. In order to find consilience, the independent agreement of independent data sets. And so we looked at these documents, documents as old as 1,200 years, to study in 9 different languages the production of lead around that time. And we collected all of this data very, very meticulously. And archaeologically, we also collected archaeological data in order to document the production of lead in this period. And the production of lead in this period, turns out, comes from Britain. And those triangles there are the mines of the Peak District and Flintshire and Devon. And as you can see from Climate Reanalyzer, which is a nice invention of the Climate Change Institute, the circulation, the wind, brings the emissions from these mines all the way down to our glacier for 2,000 years. And here is a better simulation, also from a colleague at the Climate Change Institute. You can see the mines and you can see the glacier. And you can see the air just falling and accumulating. As the air brings the emissions are deposited on the glacier. Okay. We triple checked that nothing else could be stopping that circulation. We triple checked with our data, and all of this plot says is nothing's happening in this period that would show a drop in concentration of other elements that would indicate that the atmospheric circulation for 5 years was in fact affected, and therefore give an alternative explanation for why we don't see any concentration. And then, because we're not happy with triple checking, we quadruple checked and looked at historical evidence of weather observations from the same period to see again if there was anything in particular, because 5 years changed the weather and therefore the deposition of lead on the glacier, and there wasn't. This is the largest database of written weather observations, all geo-referenced, that is, they all have coordinates, that exists in the world. It covers 1,500 years, and it will be soon mapped for everybody to use on our digital atlas. That is one of the flagship projects of the Digital Humanities at Harvard. And so we finally...
Largely by Harvard undergraduates, some of whom are in the room.
There you go. Produced largely by Harvard undergraduates. So we brought everything together, all these data sets together in one figure. This thing took 3 months. And we used, for the first time, the highest resolution atmospheric record in the world, which is the one that is produced by the Climate Change Institute with the laser data, with the laser system. And this is it. It's much, much more detailed, as you can see. And these are the mines in squares. And you can see that as the pandemic, right around 1348, hits the mines start decreasing activity, they start closing, and as the mines close, so goes the lead concentration in the ice core, and as the mines start up again, so does the lead concentration in the atmosphere. So in fact, to use Professor Ayers, we have lived in a leaded society for 2,000 years, and it has been accumulating for 2,000 years. So what? Well, when 40 to 70%, this tells us that when 40 to 70% of the population stops mining and smelting, we have the first insight into what clean air should be. This is the first insight. This works for other chemicals as well that we haven't considered yet, and we will be publishing in the future. This 5-year period is the only time the air has been clean without lead. Either to compare the current levels, well, we detected 0.01 at its lowest during the pandemic. The most recent measurement that we have is 79 nanograms, that's 3 orders of magnitude higher. And at, well, our peak was 73, you said 75. Our peak here is 73, probably because it's European. And it was 7 orders of magnitude higher. Okay. We published it with in the American Geophysical Union's new journal, GeoHealth, And it is still the most downloaded, most accessed article of the journal. And we got quite a bit of attention for it, from both good and bad. And that's it. And I would like to thank my my colleagues, my team, and the best team that one could possibly wish for. And we will all proceed into the Q&A. Thank you so much.